Alrighty, now you might notice some friends here in the camera, so we'll talk about that here shortly. But I want to talk about the next type of inference procedure, which is hypothesis testing for a matched pair sample. Now, confidence intervals are used to estimate the population parameter. From the previous lesson, we were estimating the mean difference, otherwise known as the average difference, for a matched pair's design. With hypothesis testing, we are aiming to evaluate if there is any significant evidence that would claim there is actually no difference in the pairs. Thus, our null hypothesis is that there is no mean difference, or that the mean difference is 0. Now, the reason I bring these two fellows up, this is a very common houseplant, pothos or pothos, depending on where you're at, but I actually propagated these two plants off of the same original plant, which means I took a few cuttings from a node. So I took this little piece here, put it in some water, and then let it root out, and then replanted them, and I was able to get two really awesome plants from it. Now, I wanted to conduct a matched pairs observation with this, so what I did was I gave them the same amount of sunlight, but where I differentiated was the treatments. So, for example, this very lush and lengthy and bushy pothos is now, he's growing really good, and he is getting distilled water, whereas this pothos, maybe not as luscious, still beautiful in his or her own way. This one was just getting regular tap water. But you can see there is a difference here because this one, although it's more lush and bushy, is typically a lot shorter. And then this one here that's been getting the tap water is long, it's lengthier. So my question was, did the treatment actually change how these two plants would have developed on their on their own natural variation? And so a matched pairs design was appropriate for this because it's the same experimental unit receiving two treatments. So let's take an example here. I haven't named these, so I guess I'll ask my class what we should name them, the class pets. But let us take a look here at an example of a matched pairs type of experiment, similar to the one I was describing. Now here, makers of a new pain-relieving medication claim that there is chronic pain faster than the current relieves chronic pain faster than the current top-seeking pain reliever on the market. A double-blind experiment was conducted in which 10 people who experienced chronic pain were randomly selected to take either the new or the current medication. Each of the 10 people recorded the time in minutes from taking the medication until pain relief. After an appropriate time period, each of the 10 people took the other medication and recorded the time from taking the medication until pain relief. The medication each person took first was randomly determined, and because both medications looked the same, the people in the study did not know which medication was taken first. Double blind, or actually single blind. The table below shows the summary statistics of the results, and a dot plot of the results reveals no extreme skewness or outliers. Is there significant evidence to claim the new medication is effective in lowering the average time until a person experiences pain relief? Now, here, we're going to use the phantoms model, or state plan do conclude, depending on your teacher and where you are at. But the difference has been defined. I'm told that there's no extreme skew. This definitely appears to be an experiment. 1, it says experiment. But 2, we can see that the person was randomly assigned the treatment, and then one person took both treatments. So this is definitely looking like a matched pairs style question. And lastly, we were given the difference here. So this will actually help us out. This pretty much gives us everything we need to be successful. Now I'm going to define my parameter here. I'm actually going to work this one live with you. So here, mu d is going to be the true average difference of time of pain relief. Sorry, y'all, I'm looking at my notes in the corner and trying to fill this one out live. Now we know that mu d equals the new minus the current. And if I want to see that if it's lowering the average time, meaning I want to see that which one of these has a smaller mean, the new one or the current one. So currently we suspect this. We suspect that it equals 0, meaning there is no mean difference. Now, if the new is greater than the current, we just saw an increase here. Or not an increase, but that, okay. So this is where it gets kind of wonky. because we're measuring the time here. So we want the new one to be more effective, but we want it to be effective in a way that lowers the time. So this wouldn't be the alternative that we test, because this means that it actually takes more time for the new relief to work. So we're going to want to test this situation here, where new is less than the current. And if that's true, by definition of n minus c, here n minus c would be less than 0. So I'm going to test the following null and alternative. So my null hypothesis is that there is no mean difference, and my alternative hypothesis, as we just saw mathematically here, I want it that the new medication, it happens quicker than the current medication. And so mathematically, if I rearrange this, I get this inequality here. And I'm going to use an alpha level of 0.05, the probability of my type 1 error, because it was not specified in the problem, and 5% just seems to be one of our magic numbers here in AP Stats. Now we're going to check a few of the assumptions, and we should be checking 4 assumptions, right? Our independence, our normality, and our randomness. So here, so we've done the P and the H. Now we need to check the assumptions and name the test. So here in the assumptions, we were told that there was random assignment of both pills to the 10 patients. Okay, next up, we can assume since each pair is observing their own changes, the results are independent. Since I'm taking the pill, it should have no influence on the results of you taking the pill. Next up, so we've got random, we have independence. We're not sampling, so we don't need to check the 10% condition. The last one's the normality condition, and we were told that since the dot plot reveals no extreme skewness or outliers, well, that means that the normal model is appropriate. That's condition 3 of our normal conditions. And then we'll say, since conditions are met, we use a paired t-test or match pairs t-test for a mean difference. All right, and now actually I didn't put this in the notes, that was my fault, but on your paper up here, let's just go ahead and write in the test statistic that we'll use. So very similar to one sample procedures. So I'll write this here in blue. Essentially here, T is going to be the sample statistic minus the parameter divided by the standard error. Now, note here that we claim that the mean difference is 0, so we can actually ignore this part of the formula, and to find our test statistic, we will take the sample difference, the mean of the sample difference, and divide that by the standard error of the differences. So in the same way, we're going to apply that here to our situation. So I'm going to put t as xd over s and the square root of n, and I'm going to use the following formula, negative 0.425 divided by 1.395 over the square root of 10. And if you do this in the calculator or by hand, we get the following result of negative 0.9634. Here my degrees of freedom is going to be 9, since n is 10. There were 10 pairs, or 10 participants. Now, to find the p-value, this is a probability statement here. So I want the probability, since we're checking the alternative is less than, I want the probability that our test statistic, that we get a result as low, if not more extreme, than the test statistic we found from this sample. And when I check the probability statement of that here, I get a p-value of about 0.1803. Again, the t-test statistic and the p-value both come to us from the calculator, but these are the mechanics behind it, and it's still important to recognize this for the multiple choice section. But also, ignoring the AP exam here for a second, just being a good statistician and a good mathematician is communication of what you're actually doing in your process. Well, if the p is low, we reject the null, but alas, the p is not low here. So if the p is high, you cannot deny. So here, since p-value equals 0.1803 is greater than alpha, which we specified to be 0.05, we actually fail to reject the null hypothesis, meaning there is not sufficient evidence to claim the new medication is more effective in lowering the time needed to experience pain relief. Why can I not spell? Lowering the time needed to experience pain relief. Claim the new medication is more effective in lowering the time needed to experience pain relief when compared, because it's a comparative study, to the current medication. There we go. So that's how we'd run a phantoms procedure or hypothesis test for a paired t-test here. So you can see we still define the parameter. We create our set of null hypotheses. There's a little bit more math here in determining the direction. So again, less than meaning one treatment is quicker or has less of effect than another, or greater than is the opposite, and then the not equals to is just saying that there is a difference. Now we check our conditions, either random assignment or random sampling. 10% condition if we're sampling without replacement. Independence if we're using a comparative study between populations. And the normal condition, which can be met by the population, the set being normal, the central limit theorem, or a graphical display of your sample data. If all of these conditions are met, we'll use a paired t-test where we compute the following mechanics. And then based on our p-value, we have to make a decision in terms of the null hypothesis. And then once we make a decision in terms of the null, we either do or do not have evidence for the alternative. Now, since here we're failing to reject the null hypothesis, this could potentially be a type 2 error where we fail to reject the null, but the null may actually be false. So here's another example for you. This one is not too big on the inference, but it's got some follow-up questions on what you might see on a typical inference question. So usually they'll have you compute the procedure, but then one follow-up or one pre-question could be, what does it mean for the results to be statistically significant? What are some potential confounding variables, etc.? So here I'm asking you which type of study, observational, census, survey, experiment. What's one potential confounding variable? Which hypotheses would we use? Would a significant result allow us to conclude it's effective? And what's the difference between a two-tail and a one-tail test? So I'll give you a few moments to work on that. But when thinking about confounding variables here, back to our plant friends, I couldn't really figure it out because they came from the same plant. They have the same amount of sunlight. The only difference was the treatments. What on earth could be the confounding variable? So then I thought, is it the soil? But I used the same soil. The only confounding variable I could see is that one of these guys has a terracotta pot, which dries out quicker, and the other one has a plastic pot, which tends to retain moisture a little bit better. So, I don't know, is that a potential confounding variable? Is that why this one's more lush and this one's a little skinny, tiny but mighty? Who knows? So, while Mr. Pinto ponders these wildlife questions, why don't you go ahead and try out the following examples? And then we'll come back and review. Okay, so hopefully we're able to work through some of these questions. Well, here it looks like participants are just recording the differences that they noticed. So this would be an observational study since we had no random assignment of treatments. Here, everyone is just taking this water and then we're observing the differences. What are some potential confounding variables? I also added in the biases, and this is again non-sampling error. So these aren't the official answer. The official answer is this third point here for lifestyle. Perhaps they have different dietary restrictions. Maybe they have different exercise levels. Maybe their current health conditions all vary. So this type of study hasn't accounted for these types of confounding variables. And then here's some other examples of issues with the study or flaws. What hypotheses would we create? Well, if we define UD to be the true mean difference of weight loss, I'd want my before weight to be greater than my after weight because we see in the other situation here there's no weight loss. So this would be the hypotheses I use. Would a significant result allow me to conclude? Well, no, I can only tell association from observational studies from the population from which I've sampled. Here it was volunteers. You need a well-designed experiment to infer cause and effect. And then lastly, two-tail test gives me 0.38. So if I solve this mathematically, I'd get 0.14 for a one-tail test.